Bismillahirrahmanirrahim. My name is Safiullah Mayar. Today I'm going to do my control system homework number 4. So let's start from question number 1. Question number 1 says that we have a transfer function which is open loop gs time h of s is equal to k over s plus 2 s plus 4. So first of all we need to find we have to draw a root locus diagram. So for drawing this we have to find first some elements like poles or zeros, or so after that we can use we have to find the angles. So that's how we can draw our root locus drawing. So we have open loop poles and zero. We have let's come to poles. We have 3 poles which is equal to any s that make it this equation equal to 0. So s is equal to 0, s is equal to -2, s is equal to, these are the roots of this function. So anytime the s is equal to -4, this will become 0, and this Euler function will come to 0. So these are 3 poles of this, and 0, let's try to find 0. As you can see here, we have none 0 here. So number of poles, as we say, we have 3. So now at first we have to find here if where the number of poles plus zeros to the right is odd, so we will take a few of them. So like for example, we can say from -infinity to -4, this is root 3, -4 plus -2, its combination is 2, and -2 and 0, this is equal to 1, and 0 and infinity is equal to 0. So as we can see, we don't take even, so we don't take evens, so this will be cancelled and this will be cancelled. So we will say like this is available and this is available. So this will help us. So our function goes from -infinity to -4, and from -2 and to 0, our transfer function is available. So we have root locus on this. So since we have to find asymptotes, so asymptote is equal to n minus m. N minus m, as we see, the number of folds is equal to 3. So let's find our theta. So theta k is equal to 2k plus 1 times 180 divided by 3. So this 3 goes with 96. So we can say our theta is equal to 60 degree, 180 degree, and 300 degree. So if you put 0 here, we will have 60 degree. If you put 1, so it will equal to 180 degree. If you put 2, it will be 300 degrees. So now one circulation is fine. If you go back, and it will be over 360, so we will not take it. These are our angle. So let's centroid, find centroid. So it's equal to sum of the folds minus sum of the zeros divided by n minus m, which is equal to 3. So as we don't have zeros, so sum of minus 0 minus 4, these are our poles, divided by 3, which is equal to minus 2. So S is equal to minus 2, as we can see here. So breaking point we have 2. So characteristic equipment, so let's find the breakaway angle. So for finding this, as we have our transfer functions, we will take like k is equal to minus s plus 2 and s plus 4. So from here we will take the derivative of this, take over ds is equal to 0, and we'll make it equal to 0. So it will be equal to if we make it larger, so it will be s3 plus 6 squared plus 8s minus, this will all equal to 0. So 3 after the derivative of 3s squared plus 12s plus 8, we take the derivative. So s will be equal to minus 12 plus minus, this is later 144 minus 96. This is algebraic equation. So s is equal to minus 0.845 or s is equal to minus 315. These are the roots of this function. So as we know, this point is not available between this point or this point, but this point is available between this one. So this is our valid break away. So let's see our imaginary axis crossing stability limit. So s, we'll write again, s with the power 3 plus 6 s squared plus 8s plus k is equal to 0. So root area is equal to s3 1, and we take 8 s square, we take its and k, we have s with the power of 1, 4k minus 4 8 minus k with the power 0, and then we after that we have 0, and then we have 0 with the power 1 with the coefficient of k, and we have nothing here. So this is how we can find our stability condition. So k, by this we can find 48 minus k is bigger than 0 and k is smaller than 48. So imagine axis crossing at k is equal to 48, as we can see here. So and s, as we can find, 6s squared plus 48 is equal to 0, s is equal to plus minus g. This is our imaginary part. So as you can see here, now as we have all our poles and angles, which is things are important, this minus 2 and an infinity, this one and this one is important. It's needed drawing on our angles, like here we have, this is important. Our value for the k is important. So this is how we can draw our root locus diagram. So let's start with our root locus diagram. So this is mine and infinity, this is 0. So we will put our point here, which was 0 and -2. This is -2, this is -4, and this is infinity. So for drawing, so as we say, the valid points are this one and this one, between this and this. So these are our poles, 1 2 3. So now our angle come from here like this, going through this one, because minus 0 point, how much it was, 845 is only valid in between this point and this point. So, and our k is also equal to this is our imaginary axis, this is our real axis. So as we can see here, this go like this. So this is our root locus diagram. So let me show you from what we done with our MATLAB. So this is our code with the help of AI. I have driven a code. So let's run this with the MATLAB. So we will see that our root locus is drawn here. As we can see, this is -4 and it goes to infinity. So, and this is between 0 and 4, with the point that we can see here was 0.896, as we can see here, pole. So if we change here some numbers, for example, if we change this to 5 and make it run, and we will see that our second we have changed this. As we can see, we changed this. Now we have some more changes here. We will change this to a little bit big number like 10, then we'll run it, and then we will see changes on our root locus diagram becoming more thinner. So it becomes to 0.77, something like that. So this is our first homework, first question of our fourth homework. So now we'll go to our second homework. Let's do problem number 2. In problem number 2, we have 3 amplifiers with output, operational amplifier, output 1, output 2, output number 3. So, and we have our waves so the three amplifiers connected the waveforms. So we have a waveform like this is our input, Vn is equal to, from 1 it's stable, so our Vn is equal to 1. So let's check out the second one is our first V out 1, or output 1. So it have 0.5 and it is constant. For third one, we have another waveform. It is different from its starting point to ending, so it is 4. And our third one is, this is our output 2, and we have our third output, which is also stable, which is having -1 value, output number 3. So the first, draw the appropriate connections and the parameters. So let's start what we have here. At first we will do find the V outs. As we can see, these are connected in parallel with each other. So let's try find our types of our operation amplifier, which type of these are. So for first one, its output is constant 0.5, constant, not changing. For the second one, it is changing from 0 to 4, so not constant. This is an integrated operation amplifier must have capacitor inside it, so it is a inverting amplifier, integrating amplifier, and this have also a output with -1, so this is also constant, so it must be inverting amplifier. Inverting integrator and inverter on an inverting amplifier. So this was our first job to do here. We should approach the connection parameters. So we can say that V of 1 is equal to output 1 is equal to V, as we have the formula V out over Vn, or we can say AV gain is equal to minus RF over Rn1. So at here we have output is equal to minus RF over Rin times Vin. So we can say this output, we have our output which is equal to 1 for the first one, so we can put Vn is equal to 1 and our output is equal to minus 0.5, so Rf over Rin is equal to 0.5. So let's comes to amplify second one, inverter. For inverter amplifier, we can say like V out is equal to -1 over RC Vn t dt. So we can say our Vn must be equal to with the V out of the first, or we can say V1, V out 1, V output of the first amplifier. So we can say like V out is equal to -1 over RC integration V out 1 t dt. So we can say for forming that one, so as we can see, for VO2 is equal to 4 volt at 4 seconds, t is equal to 4 seconds, it's 4 seconds is equal to this one. So for slope, if you want to find, so dv over dt, which is equal to 4 divided by 4, will equal to 1 volt for second. And this is volt, this is second. So thus we can say like 0.5 over RC, this all part is equal to 1. So this we put 0.5 our output 2, we put it here, our RC is equal to 1, so our RC is equal to 0.5. So let's go connect to the third one. So as far as we know, our output for the second one was equal to 0.5, slope was 1, so let's say VO3 is equal to RF over Rn times VO2, because it must be Vn, but we put here this value, so as 1, as it's equal to 1 minus 1, so but constant -1, meaning that the ramp has been converted into constant, so this amplifies the third stage effectively as differential or gain applied to starter, so must be constant in the control system. So inverting amplifier with gain of -1 acting on a limited signal. So let's see. As we can see, this RF3 is equal to RF1, so this is equal to 1. So let's start with the B say parallel connection transfer function with connection of parallel. So G1 is equal to -0.5, G of 1 is G of 2 is equal to minus plus 1 over s, and you can see here, and G of 3 is equal to -1. So GS a total parallel sum is equal to G1 plus G2 plus G3. So G of sum of total is equal to -0.5 -1 plus 1 over s, which is equal to -1.5 plus 1 over s. So this is our like PI type controller, so we can change it to PI type controller. So GS is equal to KP plus KI over S, as KP is equal to -1.5 and KI is equal to 1. So this is our answer for this one. So now they ask for MATLAB. So as I have written the code from help of AI, so let's see like what do we have on our MATLAB. So let's copy the code here. Let's make new, Control V. Let's run this, save. Let's make it 1, save. So as you can see, so this is our MATLAB code for second question. So let's run this. This is our, as we can see, 1 divided by s minus 1/4. This is the total parallel signal. So as we can see here, it goes from with the slope of 1, it goes upward to the when the time is we are in 2 seconds, second 2, it's equal to 0 point something 4 5, and go like this. Anytime we change the time, our signal also varies with that.